So what excites me about this project is that it's a little bit out of the box. It's an area of research that a lot of people have worked on for a long time, and people have produced a variety of different types of results based on observations, but there aren't well-established physical mechanisms to explain some of these observations. And so another aspect of this project that excites me is that it's so interdisciplinary, and that we've had to gather a group of scientists together that come from very different areas of atmospheric and space research to work together in a way that they probably wouldn't have dreamed of before. And so we have people who work on the behavior of clouds, lightning, but we also have space physicists working on the interaction between the solar wind and the magnetosphere and the ionosphere. And not only that, but we cross disciplinary boundaries in that we have to work with electromagnetism, we have to work with chemistry, we have to work with other aspects of science that are usually not combined together into one project. And so that's part of what makes it interesting to me.
So we're looking at the role of thunderstorms and electrified clouds in the global electric circuit. So a cloud doesn't have to actually be producing lightning to be electrified. And there's what we call a Wilson current that generally runs from the top of the cloud into the ionosphere and helps feed the global electric circuit. So in the typical thunderstorm setup, it's a source of charge. In the reverse setup, or the opposite polarity, it's generally a sink. So we're hoping to find some parameters of thunderstorms, like we're looking at the speed of the updraft and how much ice is in there, and we're hoping we can relate that to how strong or weak the current is.
satellite, you're thinking something the size of a car or bigger. It's the size of a loaf of bread, and that's our satellite. There's been some evidence that lightning produces gamma rays, and this is really the first satellite that's going to go out and investigate if and how and where and everything associated with gamma rays coming from lightning. Looking down at Earth for these terrestrial gamma ray bursts.
Deep within their roiling clouds, thunderstorms hold an elusive surprise. Under just the right conditions, they produce some of the highest energy radiation naturally found on Earth, terrestrial gamma ray flashes, or TGFs for short. Studies by NASA's Fermi Gamma Ray Space Telescope have shown that TGFs fire up about 1,100 times a day. Now, new research combines Fermi detections with ground-based radar and lightning location data. These studies show that TGFs come from more diverse types of storms than previously thought. In a thunderstorm, collisions among rain and snow cause different parts of the cloud to develop positive and negative electrical charges. When the strength of the electric field overcomes the insulating properties of air in the thundercloud, a lightning flash occurs. Most lightning occurs entirely within the cloud and is called an intra-cloud flash. All lightning produces a strong and sudden change in the storm's electric field, but the upward portion of an intra-cloud flash sometimes sends a surge of electrons rushing toward the upper part of the storm. Reaching speeds nearly as fast as light, these accelerated electrons give off gamma rays when their paths are deflected by air molecules. Using global lightning location networks, scientists can determine the TGF position more accurately than with Fermi data alone. 24 localized TGFs occurred within areas covered by next-generation weather radar systems. This gives scientists the opportunity to begin studying the kinds of storms that produce TGFs. These slices of radar data capture different types of storms encompassing a wide range of updraft strengths. Even the weakest of them produced a TGF. Another finding, TGFs seem to occur in the same altitude range, between 7 and 9 miles high. Lightning can form at much lower altitudes, so there's every reason to think TGFs can too. But gamma rays from TGFs occurring deeper in the atmosphere are greatly weakened. They're too dim for Fermi to detect, which probably means the satellite is undercounting them. TGFs may be far more common than we think. With this knowledge, scientists can design experiments to track storms and study how TGFs relate to their strength in evolution. This will give us an even better understanding of planet Earth's most powerful natural particle accelerator.